fingertips above the water, you watched me drown. You could have saved me, but you let me down, yeah.
Coop, thanks for being here.
Sure. Yeah, happy to be here.
Oh, I appreciate it. This is going to be a lot of fun for me personally. First question I want to ask you is it practical for us to assume that the largest things we know in the universe, planets and stars and of all magnitudes, can we relate to physics in that scale the same way we can with, I don't know, atoms and molecules? Is it all kind of interrelated?
Yeah, that's something that we really take for granted nowadays, but that wasn't always the case. I mean, it's kind of amazing that in the same sort of framework of cause and effect, the conceptual framework of physics, that you can apply it to what's going on inside of a star that is like a million light years away, and you can apply it to how, you know, a tea kettle boils, you know, a pot of water or something like that. And, you know, at first that wasn't the way we thought about nature. We originally thought that nature was made of very different things. There was like air and earth and fire, and then the heavens were its own sort of thing that had its own laws. And it actually wasn't until these Islamic caliphates between like 700 and 1200 AD that the philosophers in like Baghdad and Damascus really started trying to make the claim that if we have a theory for how rocks roll down hills, that theory should apply to the moon, and it should apply to things that are untouchable up there in the heavens, and that we should have one system that describes everything. And someone who was kind of brought up in a physics tradition as an undergraduate and graduate, this was like all kind of like, yeah, duh, that's the whole point. That's obvious to me. But I remember one time whenever I was making some claims about supernovas to my dad, like on the couch at home after graduate school one time, he was just like, yeah, but like, how do you know that? And I was like, and I kind of said, well, you know, nuclear physics has these rules, blah, blah, blah. He's like, yeah, but that's like really, really far away. Like, we've never been there. We've never. And like, he brought up a good point, which is like, why do I have confidence that I can do an experiment here on Earth to understand nuclear physics, and then take that experiment and then apply it millions of light years away to some nuclear furnace inside of a star? And it's the answer to that is like kind of subtle. Like in one regard, you're right. Like, I can't be completely sure because I don't know what it's like. I've never been inside of a star.
Okay.
But what I will say is that because everything is so intimately connected, it's just almost impossible that we would be able to understand a system here and then see exactly what we expect to see up there, and for that not to be the same sort of thing.
Okay.
Like, for example, you know, you have all these sorts of different lights here in the studio and stuff. If you just had a gas that was an atom, make it, say, sodium or something like that, and you heat up this gas, it doesn't just shine all sorts of different frequencies of light the way that like a hot incandescent light bulb does. It shines very specific frequencies of light.
Okay.
In particular, it shines these very particular kinds of like orangish yellow, and that's why you see like industrial lamps and like highways or all of this kind of orangish yellowish tinge. And when we look up at stars, we can look at all the different frequencies of light, all the different colors that are coming out of these stars, and we see exactly that kind of yellow. We could separate it exactly out, and we can predict like how much of it should be there, like how much of this light should be coming from objects of certain temperatures and certain compositions. And we see that, and it confirms to us that like, yeah, I had this thing on my desk, this sodium lamp, and I make it glow, and I pass it through something that separates all the colors, like a prism, just like the Pink Floyd. Right. I see exactly this specific color, and then I look up there, and there it is. And so that's just one of a million things that are just like, yeah, this is all kind of one big picture that's all tied together.
So light probably, we're using light as a reference point to try to prove.
It's like a fingerprint almost of an element, which is really cool. Like, so why is helium called helium? Like, this is some, I guess, Greek root, helios, like for sun. And it's called that because we found it on the sun first. Like, there isn't a whole lot of helium in our atmosphere.
Interesting.
But we saw the kind of light coming from the sun that would be this atom that we later will identify as helium. And of course, helium is in other places on Earth too. Right. But yeah, so there's just like little situations like that where we come up with a theory on Earth, we apply it out there, 150 million kilometers away, and then what we learn out there, we can actually bring back to Earth and be like, oh, that's that stuff that we see in the sun. So the inference goes both ways. We learn things about the cosmos, and then sometimes the cosmos teaches us things about here.
So while we're still being astronomers, probably, and theoretical physics, I can't pronounce that, as yourself, you're probably still being astounded as time marches on, the things we're discovering out there.
Oh yeah,
constantly.
Yeah, the rabbit hole goes really deep.
Okay,
it's really,
but we're also, the rabbit hole is continuing to go. We're still continuing to go down the rabbit hole on the smallest scales as well too, and that's part of what Cern is.
Yeah.
The particle collider, which I think, I would assume most of the people watching this probably have heard of it anyways.
Yeah.
Talk a little bit about that?
Definitely, yeah. So this machine that's on the border of France and Switzerland, it's at the Center for European Nuclear Research, the Cern, and the machine itself is called the Large Hadron Collider.
Right.
And it's this like 26, 27 kilometer in circumference ring. And it has these super high power magnets, and it just pumps energy into a beam of particles, causing them to go faster and faster and faster and faster.
It's miles long, right? It's circles, like how many miles?
So, 26 kilometers, so that would be like maybe like 15, 16 miles, something like that.
Right.
And it straddles the border. Part of it's in France, part of it's in Switzerland, so it's really huge. So it basically accelerates these things to very close to the speed of light. Maybe like 1 part in 10 million or something away from the speed of light, and smashes them together. And when they smash together, what comes out are all these new particles that we may not have seen before. So that's not maybe very intuitive, so let me kind of unpack that a little bit more. So when you want to learn what's inside of a microwave oven, you could, in principle, take 2 microwave ovens and like smash them together, and they explode, and then you could like pick out the little parts and be like, oh, this is inside of it, this is inside, right?
Okay.
And that's the way that a lot of times people will describe these particle smashing experiments, and that's like a decent sort of analogy, but it's actually a little bit more interesting than that. If you take 2 microwave ovens and you smash them together, you could actually learn what's inside of a refrigerator and things like that too, because of the following thing, and that's E equals mc squared. So you've probably heard of this equation, E equals mc squared.
Einstein, right?
So the consequence of that is that if you have enough energy, then that energy can be used to create mass. So energy and mass can kind of go back and forth. So we've seen it in the other direction, mass turning into energy. That's a nuclear energy. That's like the atomic bomb. But energy could also be turned into mass. So what that means is if you smash things together hard enough, you can create new things that weren't in the microwave in the first place, right? And so that's what we're doing. We're basically taking protons, which are the positively charged particle inside of the nucleus of an atom, and we're smashing them together so hard that they create so much energy that new particles that in some sense weren't inside of a proton and are just created, and then we can measure their properties and learn about them.
Well, where does that end? So the idea is they're trying to identify additional new properties, right?
Yeah, they're trying to find new, heavier particles which need more energy in order to discover them. And so that's why we keep building bigger and bigger rings to smash things harder and harder to find heavier and heavier particles.
What's the Higgs boson for layman purposes? Can you explain that to me?
Yeah, I could try.
Okay.
So we have this thing called the Standard Model of Particle Physics, and
that's traditional. That's the traditional model of physics, the Einstein and that group. Is that right?
That's our best understanding of what the world is made out of and how those things interact with each other on the most like smallest fundamental scale.
Okay.
Is that everything is made out of a collection of these particles, and that the standard model tells you what these particles are, what their properties are, and it also says how they interact with each other, like if you bang them off each other, what happens.
Got it.
That's not to say we're done, right? It's still very difficult to take those rules and figure out like why life exists and things like that. But that's like sort of at the base of everything. There are particles, and these particles interact with each other. So what is the Higgs boson? The Higgs boson is one of these particles in the standard model of particle physics, and it plays a very important role in that the way the standard model of particle physics works, all of the particles that are in the universe actually don't usually have mass. So there are these massless particles.
Okay.
And I say that's like kind of strange. Like
that's
a
different.
rock has mass, right?
Right.
But a way to think of it is light can be thought of as a particle called a photon, and a photon is a truly massless particle, right?
Okay.
What that means, I mean, it still has energy, and so in a sense it can still like hit you and impart energy and things like that, but it basically means it travels at the speed of light. Things that are massless move at the speed of light. So everything in the standard model is massless, but when it interacts with the Higgs boson, they acquire mass. The Higgs boson is almost like it's like a viscosity that the particles are traveling through that slows them down.
Okay.
And the effect of going slower than the speed of light is like having mass.
Okay.
And so that's why I say the Higgs field, like the sort of influence of the Higgs boson, gives mass to the particles of the standard model.
Okay.
And what's really amazing about it is that we came up with this mechanism that some other particle could give mass to other particles. We came up with this in like, I think it was 1967. It was a super long time ago.
Wow.
Peter Higgs is very old right now. And so this was like in the late 60s that he came up with this.
Okay.
And it was such a simple, elegant mechanism for giving mass to all the particles in the standard model. And it respected all of the rules that the standard model had that were really hard to try and like get around. That we basically were just like, yeah, this has to be how nature is. Nature's got to be like this. There must be a particle that does this for the standard model. And whenever we sort of worked out more or less how heavy this thing should probably be, it came out to be extremely heavy, like 125 times heavier than a proton. And a proton is 2,000 times heavier than an electron, so this is a very heavy particle. We were like, oh, we need to build a machine that can create that much energy to pop one of these things into existence to measure it.
Didn't we have one in the States? Fermilab had something smaller?
Yeah, Fermilab had what was called the Tevatron.
Okay.
And they were hoping that maybe they could find the Higgs boson there, but it was not quite enough energy to actually find it.
Okay.
And so, yeah, so we realized there's this particle out there, probably. Just from theoretical mathematical principles, we thought this particle should exist, but we knew that we didn't even have the technology. It wasn't even in existence to find this thing yet. But we started doing the research to build the technology to build this machine, and it took us 50 years before we like realized theoretically this should exist, before we invented the technology necessary to build a machine big enough to smash things hard enough to find this thing. And then we spent billions of dollars, built this machine, looked at the data, there it was.
There was, yeah. So there's validation.
Yeah.
There was validation.
And that's like something that's like really, it's not just sort of, you know, philosophical hand waving where we're just kind of explaining experiments with these like interesting stories or metaphors. Like these have predictive power, these stories. Like the more recent example than the Higgs boson was detecting gravitational waves. So have you heard of this? Yeah.
I have. Don't quite understand the whole thing, but that's been a recent discovery. Is that right?
Yeah, yeah. So do you mind if we go down that path for a second?
Great. Before we go there, let me ask you a question.
Sure.
Can we touch on, before we go there, can we touch on the two things? A photon is a particle and a wave, depending upon when we, or if we observe it. Is that correct? Am I stating
yes.
that correct? Because I'm real confused on that.
It's very, it is.
I try to wrap my head around it. Now, and that was done in the 30s or 40s, right? There's a split test or something, split something test, I think.
There's the double slit experiment.
Double slit experiment, that's it.
So the double slit experiment was actually in like 1803 or something. So this is like this guy Young from the UK. But that kind of made people think that light was a wave for sure. So it's basically, no one knew what light was. Originally, people thought light came from your eyes and was emanated outwards. And then Newton came along and was like, no, light is just these little particles of things that are kind of flying around.
Which was an educated guess on his behalf, right? For how far back that was.
Exactly. And it had explanatory power because he would draw these lines of where these particles of light would go, and those became like how we understood optics, like how we understood lenses and mirrors, like lines of light bouncing off them.
Got it.
So it was a reasonable picture. A contemporary of his, Christian Huygens, who's a Dutch physicist, was like, no, light must be like a wave, like it must be some perturbation of something that's traveling. But Newton was a rock star, and so everybody believed Newton. Right. And then in the early 1800s is whenever they did this double slit experiment. So the idea here is if you shine light onto two little narrow slits, then the light coming from the two slits will actually interfere with each other and will create this pattern that you wouldn't expect from particles. Like if you just kind of sprayed a bunch of paintballs, then you would see a whole bunch of paint behind one slit, a whole bunch of paint behind the other slit, and then nothing else. The screen would block everything else. But if it's a wave, then as the wave traveled away from those two slits, those two wave fronts would interfere with each other, and you'd get some spots with paint, some spots without paint. And so in the early 1800s, he did this work, and then this French guy, Fresnel, he kind of expanded on this work until everyone was convinced light was a wave. They're like, okay, yeah, light is a wave. And then we even figured out how to explain Newton's diagrams in terms of waves. And we were like, okay, cool. So this is correct. Light is definitely a traveling electromagnetic wave. And then Einstein came along in 1905. He's like, no, wait, there's this experiment that shows that light is clearly a particle. And that's whenever people started to, ask questions about, what is it, and then it was like, this is where you're talking about the 30s and stuff. It was around then whenever we finally put all this together and understood the bigger picture there.
From there, though, wasn't the standard model challenged by, I guess, and probably still is, there was in later years string theory and the other part of, there was a battle ended up being between, I think, Einstein, I can't remember who the other.
Yeah, Niels Bohr and Einstein came up. Yeah. So the wave particle thing, to kind of put a period on that for a second.
Niels Bohr.
I think the issue is that a wave is this almost metaphor that we use to describe something that's undulating, right? And whenever you say a wave to somebody, with that word comes a whole suite of phenomena. So you can imagine water waves crashing against a shore. You can imagine waves, interacting with each other and creating bigger waves and smaller waves. And so we have an intuition about what that kind of thing is.
Okay.
Right? Waves on a string, wave on, a drum head or something like that. When you say a particle, there's a whole suite of intuition that comes with that, about billiard balls bouncing off of each other, ricocheting off of walls, and we have all this intuition about particles. The truth of the matter is that light is neither of these two things.
Okay.
That at its core, the mathematics that describes light is actually something that's much more complicated, unfortunately, than both of these things. And so it's not that we don't know what light is. We have figured that out. It's that we don't have any of these classical metaphors that we have everyday experience with, that allows us, when someone says, what is light? We could say, let me go into my closet of categories of things. Okay, here's one category that you're familiar with. Like, it's a way. Like, what is...
Can't conceptualize it.
Exactly. And so what we do as scientists when we're trying to talk about it is we say, well, in this experiment, this thing that is light, that is neither a light nor a wave, it has wave-like features in this experiment. So I'm going to say, think of light as a wave passing through these slits, and then it does this thing, and it makes sense to you. And then in this experiment, I could say, well, this thing that's light, that's neither a particle nor a wave, it has particle-like features. And so I'm going to call it a particle in this experiment so that you kind of make the right inferences about what's happening.
Got it.
And so that's really what it is. It's really a failure of having a good metaphor than it is a sort of mystery or lack of understanding of what light is and how it behaves. The mathematical thing that describes light, unfortunately, is just, you just like have to like get a math degree to like get the words. I mean, you have to know what the word Hilbert space means. You have to know what a quantum field theory even is, and Lorentz invariance, and so there's a lot. What's
the battle though that I keep hearing? Trying to integrate the standard model with what is, and we haven't been able to do it yet, right?
Yeah. So the last 100 years, there's been a couple of battles leading up. There's this thing with like Einstein and Bohr. So that's one thing that we could talk about. That sort of came. It was basically 1927 at the
What was the
Slovak
crux
conference.
of the argument?
Well, the issue, I think, was that Einstein had certain intuitions about what he thought a sort of like fundamental theory of nature should be, and quantum mechanics, unfortunately, like didn't have all of those properties that he wanted, right? And so Einstein was constantly trying to figure out ways to articulate his intuition to the community, working on quantum mechanics about how this doesn't feel like it's a complete theory yet, that we're probably missing something. And then the quantum mechanics people will be like, no, you're just prejudiced because you're not ready for this like new science. And and one thing to keep in mind is it's not like Einstein hated or didn't understand quantum mechanics. Like Einstein invented quantum mechanics in a lot of ways. You could argue him, maybe Niels Bohr is another big one, or Max Planck, but Einstein's one of the fathers of quantum mechanics. So for sure,
did not know that.
Yeah, so for sure he gets it. And another common misconception is that it's the uncertainty of quantum mechanics that Einstein didn't like. It's true that he wasn't stoked about the fact that like you couldn't get these like beautiful mathematically precise answers, that you could only calculate probabilities of certain things happening. But even that, it was like that wasn't I think his main contention. I think his main contention with quantum mechanics is this property called locality. And that's a fancy word that basically means that things should only be able to interact with things that are close to them. That basically, if I want to describe what's happening in this room, I need to know what's going on in this room. I don't need to know what's going on Mars, or what's going on in
quantum entanglement
galaxy.
Is the same thing?
So this is where the issue with quantum mechanics comes in is whenever two systems become entangled, the concept of space is like irrelevant to whether these things are entangled or not. So they could be right next to each other and entangled, or they could be light years away and be entangled. And so what Einstein really didn't like was that, in principle, you couldn't treat a system of entangled things as like one system over here and one system over here. In some sense, that like feature of nature was extended over an, in principle, arbitrarily long distance. And so that's where he wrote this paper with these guys, Podolsky and Rosen. It's called the EPR paper, Einstein, Podolsky, Rosen. And he came up with the Epr paradox. And it was basically exactly this, that you could take some particle that decays into two entangled photons, and that these entangled photons could travel forever, and they would still be entangled. And if you measured one all the way over here, that would instantly tell you about what's going to happen all the way over here. And that sort of like information being connected in that way was something that didn't seem to sit well with him, at least, when he was writing all this stuff in the 30s. But that seems to be just the case, that the locality of the universe is a sort of only approximate thing in some sense.
We've done tests, like they've identified a particle here and a particle miles away, and when this particle reacts, the other one reacts. They go the opposite. Is it pretty much? I'm trying to wrap my head around it, but I think I've read an essay on that once prior. It's mind numbing to me. They don't have to be in close proximity.
Right. So it's actually, with all things physics, it's kind of subtle. So it's not necessarily that if I like move this thing, then that thing moves. Because that would violate special relativity. Like if I could have some sort of Morse code device where I jiggle this particle back and forth, and in Andromeda you feel it jiggle back and forth instantaneously, then that would be propagating a signal to Alpha Centauri faster than the speed of light. And so that's not possible. It's more of a sort of like, it's more of a state of knowledge sort of things, where it's like, if I measure this thing over here, even though you, who lives over there, would, when you do the measurement, to you there's a 50-50 chance it could be in like state A or state B. But to me, if I measure mine in state B, I know for sure yours is going to be state A. So like, that's the opposite sort of thing. It's like one's, and for this example, you could think of something spinning in this direction or spinning clockwise.
That's the example I read.
Right. And so it's like, I can know about your reality like light years away instantly by doing a measurement here. But the sort of like reason why this doesn't destroy physics is because I can't tell you that I know without sending something to you, and whatever signal I send to you is still bound by the speed of light.
I got it.
And the way it travels. So, yeah. Okay.
Well, that's deep.
So that's the first half of the 20th century. That's the battle between Einstein, and you were asking about standard model and string theory and stuff. So the current, in terms of fundamental physics, and there's a lot of different branches of physics.
Sure.
But in terms of like the fundamental, what's at the very bottom of everything, the question now is how to incorporate gravity into the standard model. So right now the standard model talks about electricity and magnetism, which is one of the forces of nature. It talks about like radioactive decay, which is called the weak nuclear force. That's another
weak
one.
Nuclear and strong nuclear.
And then the thing that holds the nucleus together is the strong nuclear force. So it talks about 3 of the 4 forces, but it doesn't talk about gravity. And the reason it doesn't talk about gravity is because gravity at these scales are completely irrelevant. And that's
why?
Exactly. That's unintuitive to us. Gravity is very important to us, right? That's like the dominant thing in this room right now, is the fact that gravity is holding everything down. But if you think about it, think about like a flea that can so easily, with a little bit of chemical reaction in their legs, can just jump off of the earth like several times its height, right? The earth is 10 to the 24 kilograms, which is like 10 to the, what would it be, 27, so 10 to the 51 particles, all gravitationally pulling on that flea, one with 51 zeros after it, pulling on that flea, and with just like, a couple million chemical reactions in the flea's knee, it can beat that, right? So the point is,
gravity's weak.
So the point is gravity's weak. The reason why we think it's strong is because we're constantly being pulled on by one with 51 zeros after it particles. That gravity doesn't have positive and negative, so nothing can cancel gravity. Like, we're also made of electrical particles, like protons and electrons, but there's the same number of protons as there are electrons in us, and so all these things cancel. There's no canceling gravity. There's just mass is positive, and everything has positive mass, and everything pulls on everything else. The kind of classic examples I like to use for this in my classes is, if you have 2 electrons, they gravitationally attract each other because they have mass, but they electrically repel each other because like charges repel, and they both have negative charge. And so a question I like to ask is, which one wins? And some people are like, well, to me, like, what keeps me on the ground is gravity, so maybe gravity wins. But then some people are like, yeah, but like we use like electric voltage and stuff to push charges around, so maybe electricity wins. And the answer is that it's not even close. That electricity wins by a factor of 10 to the 42.
Wow.
One with 42 zeros after it. So it's like, so for that reason, it completely doesn't matter in particle experiments, because the gravity is just completely negligible what's going on there.
Interesting.
Right? It's so much weaker. Yeah. So gravity is just something we don't have to think about. We have a very good theory of gravity on very big scales, and we could kind of put them together. Like, we can use our theory of gravity to say what space-time looks like, and I'll go into that a little more in a second.
I'm looking forward to that, yes.
And then you can put the standard model on one of these space-times that are created by gravity, and you could do some calculations. And that's what Stephen Hawking did with Hawking radiation. It's his theory of how black holes actually evaporate over time. So that is some weird hybrid standard model and gravity put together. But it's not like, first you do the gravity, and then you fix what space-time's supposed to look like, and then you put your standard model inside of this box that's already fixed.
I get it.
They're not reacting with each other in a way that we understand. So what is, should I go with what's our theory of gravity first? Right, so Isaac Newton looks up at these rocks floating around in the sky, and And what he realizes is that these things are on orbits, right? You know, this was, Newton was after Copernicus and Kepler and all these people, so he knew that they were just rocks orbiting around. And what he realized was that the same thing that makes rocks on Earth fall should make rocks in space fall, right? And that circular motion, these orbits, could be described by things falling and then missing the Earth, and then falling back the other way and then missing, and then falling the other way and then missing. And that what orbiting really was just falling forever. Was just things that are trying to fall, but they have so much of this tangential speed that they miss the Earth, and then they have to fall the other way to get back to the Earth, and they keep falling.
I did not know this. Okay,
yeah,
that was his theory.
That was the universal theory of gravity. A lot of people think Newton invented gravity or something like that. No, guess what? People knew before 1666 that gravity existed,
right?
But it wasn't, you know. But what was special is that he used the description of gravity, which everybody knew about, to explain why things orbit. And not just that, he invented a whole branch of mathematics called calculus so that he could calculate, using his theory, exactly how things orbit. So he derived all of Kepler's laws of planetary motion, all this stuff. He derived it from first principles using a pen and paper. And so that's like what's impressive about.
He was a genius.
He did this in his 20s. Like there was like a plague in London, and so he like went to his like country home in his early 20s, maybe 24 years old, something like that, and he just like had to live in a country home for a couple of years to avoid the plague. And in the meantime, he's like, I'll invent calculus, modern physics, you know, classical mechanics. So yeah, he was a pretty impressive guy. And so again, this is one of these, to tie this back to what we were saying at the very beginning of our discussion, the laws that explain how two rocks attract each other were derived by looking at the orbits of planets and moons, right? So
scale.
Exactly. It's like we used this deep fundamental belief that everything should be connected, and from that we were able to understand rocks rolling down hills by looking at how the moon was like orbiting the Earth. It's pretty amazing. So, but Newton's theory has a quirky thing about it.
Okay.
And that's that. Of course it does. And that's that Newton's theory had nothing to do with time. So in particular, if the sun disappeared right now, then according to Newton's theory, the Earth would stop orbiting the sun. There'd be no sun. It would just start kind of moving tangent to the circle that it was on. And Einstein didn't like that because to Einstein, things can't travel faster than the speed of light. You get into all sorts of theoretical problems.
Is that proven by math? We kind of accept that to be true?
Yes, we definitely accept that to be true.
Maybe? Well, neutrinos, they don't
Nothing can move faster than light. Yep. So we have these particle accelerators now that are accelerating particles, and they're pumping and pumping and pumping energy into these things, and we very quickly get them to 99% the speed of light, and then we pump 10 times more energy, they get to 99.9%, and then we pump 10 times more, they get 99.99%. So yeah, so we definitely have that one on lockdown at this point. And so Einstein says, no, if the sun disappeared, the Earth should still think the sun was there for 8.5 minutes, because that's how long it takes for light to
get here
from the sun to us. And so Einstein needed to come up with a way to make Newton's theory of gravity actually depend on time as well. The same way that, like, by this time, so this was in the early 1900s, the late 1800s is when we understood electricity and magnetism. And so that was already a theory that respected the laws of relativity. Kind of a not commonly known fact, relativity was discovered because of electricity and magnetism.
Oh, really?
Electricity and magnetism satisfied relativity, not classical Newtonian mechanics.
Interesting.
And so people were like, whoa, electricity and magnetism is kind of weird. And Einstein was the first one to just be like, guys, maybe Newton's wrong. You know, like maybe electricity and magnetism is right, and we've been getting it wrong all along. And so the 1905 paper about special relativity was called something like On the Electrodynamics of Continuous Bodies or something like that. So it was about electricity. So Einstein needed to find a way to make gravity relativistic. He needed to come up with a theory of gravity that respected this fact that nothing should travel faster than the speed of light. And you know, a normal person would probably just take little ways of tweaking Newton's theory to try and like incorporate these new effects, but that's not how Einstein rolled. Einstein was like, I'm going to throw Newton completely out the window, and I'm going to just, from first principles, if I was just like a person on an island, what is it about gravity? Like, what would a theory of gravity look like? And so he had this insight, which everyone knew was true, but I haven't really found anywhere in the literature where people really appreciated this fact in a really genuine way. So here's the fact. The strength of gravity is proportional to your mass. The bigger you are, the stronger gravity is. So you're pulled harder to Jupiter than you are to Earth, right? Because Jupiter's much bigger. So there's this term in the math, m, which stands for your mass. But another thing that Newton worked on was cause and effect. Whenever I push on something, how does it respond? And what his second law of physics is F equals ma. That when you push on something, it causes it to accelerate, but that acceleration is going to be inversely proportional to the mass. That if you're more massive, you have to push harder. If you're in space, you push on an elephant, you got to push harder to get it to accelerate. Right? And what I feel like no one really appreciated is that those two masses should in principle have nothing to do with each other. One is how much gravity affects you, and one is like your resistance to being moved through space. It's like your stickiness to space, the amount by which you want to stay in the same position, right? Electricity doesn't have this property. The strength of electricity has to do with electric charge, but this resistance to being accelerated has to do with mass. So those are two different things. But for gravity, they are the same. In some sense, gravitational charge is also the same as your inertial mass, this mass that determines your inertia. Right? And so what is the consequence of this? The consequence of this is that everything that's falling in a gravitational field falls the same way. Right? Let's kind of unpack that a little bit, right? If you are in space and you drop an elephant and a mouse, right, in some gravitational field, they both move the exact same way. And all of the pieces of the elephant, the particles of the elephant, all move in uniform the same way. And so what that means is that, if you're the elephant, you don't even feel gravity. And we know this is, 1905 to 1915 is when he was working on this. So this was before we went into the International Space Station and could feel this for ourselves. Nowadays, it kind of makes sense. Like, astronauts don't feel anything. It's not zero G. People call it zero G. There's plenty of gravity there. Like, if there wasn't gravity, then the space station would just fly off into space. Of course. Right? But what it is the astronauts are constantly falling and constantly missing their Earth when they're falling. Got it. And so, but they don't feel anything because all the particles in their body are all being accelerated by the exact same amount. I get it. And why is that? It's because it's not that gravity pulls on everything the same. It pulls on heavier things exactly the amount harder that it needs to. I get it. So that, you know what I mean? Yep. And so basically, if an elephant weighs 1,000 times a mouse, gravity will pull 1,000 times harder on the elephant than the mouse so that they both accelerate at the same rate. Right? Understood. And so what that made Einstein think is that gravity must actually just be a property of space itself. That it's not some sort of external thing that's pulling on you. If everything is like experiencing it the same way, then it must be like a property of the background space that we're in. Got it. A really cool analogy that I saw, I don't know if it was on the internet or a book or something, that I really like, is imagine the following thought experiment. Einstein loved these things. Like in German, it's Gedanken experiment. Gedanken experiment. So imagine you and I are on the equator, and imagine this was billions of years ago when the Earth was a giant snowball. Okay, so at one point the Earth was frozen over. And so imagine it's just solid, frictionless ice. Okay, and imagine there's no atmosphere, just to make this easy. So we're a giant sphere that's completely frictionless, and you and I are in the equator. And imagine that we're given just a little kick so that we're both being moved north. So now we're just drifting, and we don't slow down because, there's no friction, there's no air resistance. We're both just going north. And at first, we're completely parallel in our motion. We're both going north. And so our relative distance is the same. So we're both on these lines of longitude that go up, right? And so we're both just kind of like that. But what happens over time, right? Slowly, we start getting closer and closer to each other. Right? We start being attracted to each other. But it's not because there's a force, it's because we're on a sphere. And if we go north, we're eventually going to hit each other at the North Pole. And so we don't feel anything, yet we're being pulled towards each other. And if you were an elephant and I was a mouse, that would be exactly the same. If you were Mount Everest and I was
the mass
a flea.
doesn't make any difference.
So it's not that. It's somehow the fact that the space that we're on is a curved space.
Got it.
Is creating this relative acceleration that we're feeling. Because we start out slow, but as we get close to the North Pole, we start really going towards each other fast. So we're accelerating towards each other because of the curvature of space. And so Einstein realized that he needed to come up with a way to describe gravity using the curvature of space and also time itself. Relativity means that time and space actually have to be kind of connected to each other in an interesting way.
Right.
And so by coming up with the theory of curved space-time, he was able to describe all of the phenomena of gravity.
I never heard it put like that to me.
Yeah, so it's pretty cool. I mean, the classic image is like a bowling ball and a trampoline, curved space and stuff rolls inwards. But that kind of already has gravity in it, right? Because why do you fall down on the trampoline in the first place?
Exactly right.
But really, it's that we're all kind of trying to go in straight lines, but all these straight lines are curved into each other because of the fact that we live in a curved space. And that the only reason we think we feel gravity is because the floor is pushing on us, not because gravity. You don't feel the gravity pulling on you. You feel the floor pushing on you.
Got it.
So anyways, this was Einstein's general theory of relativity. So special relativity is just that clocks tick kind of differently, and relative motion causes time and space to mix in a weird way. That the speed of light is this sort of like cosmic speed limit. General relativity includes gravity into all this.
Did not know that.
Yeah.
So that's the difference.
So that's like the big sort of picture of what very large things which are dominated by gravity do.
Okay.
That's where black holes come into the mix. That's where the Big Bang and all that come into the mix.
Okay.
Is with the general theory of relativity. So two things there. One is, why can't we make general relativity and the standard model come together? But the thing that I want to loop back to, since we're here, is one of the consequences of there being a space-time that can be curved is that you can make ripples of that space-time. So if you perturb the space-time, just like you could perturb the surface of a pond, you can cause that space-time to oscillate, to undulate. You can make waves of gravity, these gravitational waves. Right? So Einstein realized this straight away. Once you have the formalism, you could be like, well, this is like some dynamic system that reacts, and all reactions have to propagate at some finite speed because it's relativistic. So there must be, this reaction must create a ripple of gravitational radiation. Just like, if you take an electric charge and you wiggle around an electric charge, it creates an electromagnetic wave, which is light, right? So gravity must have the same thing. So he did the calculation and he was like, okay, so what would sort of like, if you had like a gravitational wave passing through you, what would be the effect of that? And it's kind of hard to imagine because gravity is space changing its shape, right? And so like, what would it mean for space to like kind of expand and contract all at once? And that's like maybe not something that you could really feel, but if space expanded in one direction but contracted in another direction, you can measure the sort of relative distance between these two things. So what you could do is you could take a laser beam, you could split it apart to go in two orthogonal directions, 90-degree angles of each other, and you could have them go hit a mirror and come back, and if the distances were different for a second, then the lasers will get back at a different time. Right? And so you can have the laser interfere with itself in a way that you could tell that the distances got weird. So Einstein calculated what is the relative change in the distance from a gravitational wave from something huge like a black hole orbiting another black hole. And what he calculated, that it's 1 part in 10 to the 21, which I've heard it described as like the width of a hair between here and Alpha Centauri or something like that.
Incredible.
And so Einstein was like, okay, yes, in principle gravitational waves exist, but humans will never be able to have like the technology to be able to measure 1 part in 10 to the minus 21. Like, that's ridiculous.
And he said that back in the early 1900s.
Exactly. He was like, yeah, they're there, but like they're never going to be a thing that we use. Yeah, exactly. And so lo and behold, like literally like 100 years almost to the dot afterwards, and like 2016, something like that. It took us 50 years. It was just like the Large Hadron Collider, where we had the idea and we had to invent new technology to be able to create this gigantic armed laser thing. The arms are like 4 kilometers long.
I saw an article on that,
and we built a machine that actually is now able to see gravitational radiation from the cosmos. And so, yeah, it's pretty awesome. I mean, it's probably in the grander scheme of history. If you look at like a year 3500 like history book, it might be like maybe the most important thing that happened in our lives, is the fact that,
no kidding,
because in some sense it's akin to whenever Galileo used a telescope to look at the stars. It's just a new window through which we are able to look at the universe. So it's like we just got another sense, and we'll have that forever and can see new things. And why it's so important is because of this fact I mentioned earlier. There's no positive and negative gravitational charge.
Right.
So you can't block a gravitational wave. So there are things we can't see because stuff's opaque to light. Like, we can't see through certain things.
Right.
And that's true both, like, there are objects that you can't see through, but also if you go far enough back in time, the universe itself didn't used to be transparent the way it is now. So there's a certain time that you can go back in our cosmic evolution to where there's no way a telescope will ever teach you anything past that point. Because at that point, the universe was dense enough and hot enough that it just wasn't transparent, and so no light will ever get to us from there. And so, but gravitational waves in principle could see forever, because nothing can block a gravitational wave.
That's interesting.
So it's a really big deal. It's very exciting, the gravitational wave thing.
I think most of the public's missed it, though.
Yeah. I mean, it's kind of...
The Higgs Boson got more press.
It did. And, like, the thing is like... Yeah, the amount of press certain things get is not necessarily super well correlated with, like, how important. Yeah.
Right.
And there's a lot of just sort of, like, funding and political reasons and stuff like that. I mean, one example... in the other direction, the Higgs boson was a pretty big deal. It kind of like ended a chapter of the Standard Model. Like, we needed the Higgs boson for the Standard Model to be resolved, to be consistent,
validated.
Yeah, and it was like, good, everything checks out, particles, we got it. There's a few weird things about the Standard Model, but there aren't a whole lot of wrong things about the Standard Model.
Okay.
There's things that like suggest that maybe there's like supersymmetry and other random stuff like that we could get into.
Yeah.
But the Standard Model as itself, every single particle experiment is well within the predictions of the Standard Model. Like, particle physicists are a little worried right now because they're like, there might not be a whole lot like left to do in some sense.
Really?
Yeah, I mean, if we would have found other things like a supersymmetric particle or something, then yeah, Congress would be talking about how we're going to build the next generation of particle accelerators.
But they haven't found that yet.
We haven't. And so,
but they're still slamming particles together over there, right?
They are, and there's still a lot of things to learn about with the Higgs boson. And there's a lot of things that are at lower energy scales than the Higgs boson that are still like precision measurements that we need to like clean up. But yeah, like right now, the sort of big picture of any experiment we completely understand. But if you could potentially get like infinitely precise with your measurements, you might be able to measure teeny tiny effects from new physics that we don't know about.
Okay.
And so that's why we're still, I mean, even the US just agreed to build another accelerator. I think it's a linear accelerator in it's out by like Brookhaven National Labs on Long Island.
Okay.
And it's asking different kinds of questions, but there are still questions in particle physics to ask. But the fundamental questions right now, it's like, well, we don't really get how gravity in particle physics works, but besides that, we don't really have any clues as to like where to look next.
In the 70s, was string theory in that area of study, was it developed in the 70s? I have a picture of a guy in my mind from the late 70s, glasses, professor in Boston, I think, and then there was
Ed Witten. Yeah, Edward Witten is
Edward
glasses.
Witten.
He's at
Edward
Harvard.
Witten.
Yeah.
But before Edward, who was the other? There was another one, and there's a Valensky, I think, was
Veneziano. That might be. So
I did a lot of just watching and reading on that years ago, so even my details aren't there. But the string theory, was it challenging the Standard Model? Was it a direct challenge to the Standard Model?
No, it's actually like, if anything, the standard model challenges string theory in the sense that string theory is supposed to be this more fundamental theory that the standard model is supposed to kind of come out of.
Interesting.
The same way that, like, the kind of most visceral example is we had all these theories about thermodynamics in the 1800s, and we understood combustion engines and things. We were pretty good at thermodynamics, but we didn't know about atoms yet. We didn't know that what heat was random motion of teeny tiny little particles. And so, you know, Ludwig Boltzmann was an Austrian mathematician, and, you know, other people, Gibbs is another guy that is really big in this, but Kelvin you might have heard of. So what these people realized is that you could describe the random motion of atoms as a more fundamental thing, and out of that would emerge this theory of thermodynamics.
Got it.
And that's the relationship between string theory and the standard model. That string theory is a more fundamental theory, and if you zoom way out and look at string theory, it should look like the standard model on our pathetic energy scales and things like that. Right.
It's taken some hits, though. I mean, hasn't string theory taken its hits over the last 2 decades?
Yeah. So the story of string theory is as follows, if you don't mind me going into it.
Please. Enlighten me, please.
So it does go back to like the 60s, 70s kind of era.
Okay, thought so.
And originally, string theory had nothing to do with gravity. String theory originally was before we had a theory for the strong nuclear force. That theory is called quantum chromodynamics. Chromo, like color. It's like so before we had quantum chromodynamics, we didn't understand all of these different, like, nuclear physics particles that were popping up all over the place. We just kept finding new particles, and they followed some patterns, but, you know, we didn't really understand how they could be the way they are.
Okay.
And so what we did is we came up with a description of what would create this pattern of all these particles that we're seeing. And these two guys, Nambu and Goto, I guess they were probably Japanese theoretical physicists, realized that that pattern that these people have described actually comes from just taking a string, like a relativistic little string of energy, and then applying quantum mechanics to it. That once you take your string and then you quantize it, out pops all of these formulas that people were using to try and understand the strong force. And so, like, one of the first people to kind of work this out was this Italian physicist named Veneziano. Which I was super lucky. I actually learned string theory from him. He was visiting. I was at NYU a couple years ago, and he was visiting NYU as like a global professor, and he taught like strings there, and it was really cool. And he like told us all these stories from back in the day.
I bet.
But anyways, so Veneziano and Nambu Goto, like, these people were kind of starting to paint this picture, but what they also realized is more than just these particles they were seeing were popping out of this new theory of strings. Tons of particles were popping out of this new theory. And so most people were like, okay, well, this is wrong. Right? Because, like, for example, one of the particles that pops out has properties that on large scales behave like general relativity, behave like gravity.
Got it.
And so, you know, the uninspired physicists were like, well, the strong theory is not gravity, so this must be wrong. But the more inspired physicists were like, well, wait, why is that a problem? We just came up with a quantum theory that predicts gravity. Gravity pops out of this thing as a prediction. So this was a guy, Green and Schwartz, and then also Witten too. And they wrote this famous book in the early 80s, the Green-Schwartz-Witten superstring theory book. And they started to take this new theory and were like, what if all of these particles were like all of the particles? And what if gravity too was just a manifestation of string theory? So this was developed 80s, and then it kind of, in the 90s, we started to realize all these like subtle and interesting properties of string theory. And yeah, there were some calculations in string theory that were very promising. Like, we got the Hawking black hole formula to pop out of the thermodynamics of string theory, which was like pretty cool. But yeah, it took some hits. I would say the thing is right now is that there's no model of string theory that right now describes our universe as it is. String theory is kind of like this sandbox that you can kind of describe all sorts of different kinds of like quantum field theories. But no one has yet been able to say, take string theory that describes how things interact with each other, put this stuff into it, and what'll come out is our exact standard model, our exact space-time, and all that.
I was described as they were trying to elegantly connect the two, weren't they?
Yeah, yeah. So string theory is an example of a theory that connects general relativity to quantum field theory, which is the theory that particle physics is based off of.
Okay.
So even though it might not be the one that describes our like universe, it is an example of how that is possible. And so it is, I think, a very important milestone in sort of the history of physics. Whether people figure out how to wrangle string theory into the form of what we see, we haven't figured that out yet.
Is part of string theory also dimensions?
Yeah, so that's one thing that people don't like about string theory, is that to make string theory mathematically consistent, it can't just live in 3 space dimensions and 1 time dimension. That it actually has to have a property of it called supersymmetry, which is very mathematical, and people have tried to make metaphors for what it is, but I don't think they're very helpful. So let's just say there's a mathematical property that string theory has to satisfy called supersymmetry. And on top of that, it needs to be in 10 dimensions.
10 dimensions. So how do we... If you're trying to even describe the 4th dimension to me, where's the metaphor for an average person to get to understand where that 4th dimension fits?
Yeah.
Now you're talking about 10.
Exactly.
But just the 4th, even getting to the 4th, I think, is almost conceptually very difficult.
It is. It definitely, in some sense, it's impossible, in the sense that you'll never like feel the 4th dimension the same way that you'll feel the 3rd dimension. I mean, if you think about it, we only see in 2 dimensions in some sense, right? We actually use additional information to try and infer the 3rd dimension. Like we have 2 eyes that allow us to have stereoscopic vision, and so I have parallax that's telling me that some things are close and some things are far away, right? And I know the relative size of things, and so I could tell that really big thing over there must be far away because it looks small to me and stuff like that. So
that's all learned.
Yeah, our brain is inferring a 3rd dimension in the first place, but we're also moving in 3 directions that like imply to us that like there are 3 dimensions. So what would a 4th dimension be? So first of all, relativity is best described as a 4-dimensional theory of space-time. So not just space, but time is in some sense like a 4th dimension. And yeah, if you wanted to picture it geometrically, it's very difficult. Usually what you do in like textbooks and things like that is you get rid of one of the space dimensions, and you just think of a 2-spatial dimensional theory, like life on a piece of paper, and then think of time as being the direction out of the piece of paper.
Wasn't there a movie made on that? Flat something?
It's Flatland.
Flatland. I think it was Flatland. Yeah, and I actually watched that in an attempt to understand all this stuff. And it was you're living in 2 dimensions.
Yeah, exactly. Like think about if you kind of are able to jump from 2 to 3 dimensions, then that can help you have an intuition about what it would mean to go from 3 to 4 dimensions.
Got it.
Like for one example is in 4 space dimensions, knots don't exist. So you could tie your shoes, you could like tie a string and pull it and make it into a knot, but you couldn't take a string, this 1-dimensional object like a string, and you couldn't tie a knot in 4 dimensions. And the reason is there's just like too much wiggle room. Like you can always like move something into the 4th dimension to get it around the thing that's blocking it like in the 3rd dimension. So deep. So, and what's funny is that some people are really love this fact and think that maybe there's something special about why we live in 3 dimensions. That the fact that knots only exist in 3 dimensions might suggest to us that there's a special, like if string theory is in 10 dimensions, how did we end up just being on a 3-dimensional sort of subspace of this? And some people think that it has to do with like the way that strings can like make knots in 3 dimensions.
Wow.
I don't know. I haven't seen any sort of convincing thing about that, but there are people, and this is an old idea actually, like the periodic table, people tried to explain back in the late 1800s as like knots of like electrical energy, and different kinds of knots would be the different elementary particles, which is kind of cool. But yeah, so I don't know, have you ever seen any of these animations of a 4-dimensional cube? On the internet they have like GIFs
I have not.
things like that.
I have not.
Yeah, they try and show you what it would be like when you think of a 3-dimensional cube, you could take a square in 2 dimensions, and you could think about how as you move, like an MRI, like as you move through the cube, you kind of see like the cross section of the cube over and over again. And so what they try and do is they try and take 3-dimensional cross sections of a 4-dimensional cube, and so every cross section itself is a 3-dimensional cube of some kind.
I get it in theory, what you're telling me, but it's hard to start to like conceptually look at it and get it.
I mean, that's like we don't experience it, and so like that all you can do in some senses is give yourself mathematical intuition and things like that. And that's back to the wave-particle duality thing. That's the unfortunate part about whenever someone asks, you know, me or any other kind of scientist, like, is light a wave or a particle? Our like heart sinks when we hear the question, because we're like, the answer is if we sat down and just practiced using Hilbert space like quantum mechanics calculations, you would eventually get it, but there's no thing in your life that I could point to
relate to
that is like, it's like this thing. It's like going to the ocean.
It's not relatable.
Exactly. But what's cool is that you can build up mathematical intuition for spaces that you will never exist within.
That's insane.
And it's just like how eventually, you know, presumably little kids probably see in 2 dimensions actually. Like it's probably there is a moment whenever an infant, their brain integrates the information to the point at which they can infer a 3rd dimension from the 2-dimensional shapes they see.
Yeah.
And I think that that's a similar thing with mathematics, that like you eventually start working in some infinite dimensional Hilbert space of quantum mechanics long enough that like your stereoscopic vision kicks in and you start to like see these things. So.
All right, let me take you out to space for a second, Coop. I've asked this question and had it explained to me, I'm sure, very well by people like yourself, but I've never really, still don't get it. I'll give you a shot.
All right.
Big Bang, the best we understand, the Big Bang happened 14.6 billion years roughly.
Roughly,
right?
yeah.
So everything that we see, know, we can look out and see, everything came from, Lawrence Krauss tells us it came from nothing. It exploded, right? And all this incredible force these many billion years ago, and it's everywhere. There's no up, down, sideways, everything, all directions,
right
into it. We don't know if it's infinity, but it could be all directions. People say that, or I've read that the space is linear, meaning when you see the Milky Way, it looks linear to a degree, you know, like almost not perfectly flat, but flat.
Yeah.
We're in an orbit around the sun, and I think, are not the planets also on the same latitudinal orbit? Are we all like kind of lined up that way?
It's called the ecliptic plane.
Okay.
It's the plane that all the planets are orbiting on.
So how do we stay like if the Earth was to fall out of orbit, like let's say the sun burned up and 8 minutes later the Earth fell and we went out of orbit, how does everything just stay in that plane? And if the universe is somewhat linear, our universe linear in that, is it somewhat flat? And if it is somewhat flat, there's got to be, is it a shorter distance from the height of it than it is the breadth of it? I just don't get it, because everything looks to be somewhat flattish in the way that we see photographs, and it's confusing to me.
Yes. Okay. So the fact that things start to form a plane is actually a dynamic phenomenon of just classical mechanics.
Okay.
And it's not a property of the universe. So there are all sorts of galaxies, and they're all oriented in all sorts of different directions, and they're pretty much uniformly spread out in every direction. So there's
I did not know that.
Yeah,
Okay.
there's no sort of like plane that the whole universe is in, that our solar system's in some plane, the Milky Way is in some plane, Andromeda's in another plane, and like,
And they could be going all
right,
different directions. They could have some kind of like shape,
yeah,
but it's not uniformly
Right.
linear.
You're right.
Okay.
So the question, a better question is kind of like, well, why does that seem to happen sometimes where a direction gets picked out,
Right.
and all of a sudden there's sort of
Right.
like Saturn, for example. Why doesn't Saturn have a giant sphere of rocks around it? Why does it have rings?
Right.
And the answer is actually just has to do with dynamics, that if you start with a giant sphere of rocks, and if those rocks have some overall rotation in any direction, then with respect to that axis of rotation, everything, the random interactions will cause everything to start to orbit in
Okay.
the equator.
Okay.
And so what happens is things start spherical, but from interactions, their orbits kind of decay into the plane that is perpendicular to the axis of rotation.
Okay.
So Saturn's going around like this, and so that means that its plane is like that.
Okay.
The
Okay.
sun is rotating as well. The sun is rotating pretty fast. And if you look at the plane of the planets, we're all going around in that plane that is orthogonal to the axis of rotation of the
Okay.
sun. And the sun is orbiting around the center of the Milky Way too. Now, that's not to say that everything's perfectly in a plane. Like, things are, it takes time in order to settle into this configuration.
Okay.
And so, you could ask, why isn't the Earth just flat? And the answer is that, like, you don't necessarily settle into that configuration. There are other forces that are involved as well.
Well, why are there so many spheres in space?
Yeah, that has to do with the fact that gravity only is a function of the distance between two things.
Okay.
There's no specific direction. So if you have an object here and an object here, they'll want to come together. There's a third object here, they'll want to come together. And so things will just slowly start accumulating, and there's no reason for it to accumulate outward in any given direction, right?
Okay.
Basically, if you think about it, like, things want to roll downhill because they want to be as close to the center of the Earth as possible. So imagine if everything on
Understood.
Earth wanted to be as close to the center as possible. What shape would that make?
Got
right?
it.
It wouldn't make anything that had any sort of bump to it, because then all this stuff would want to be over here. All the stuff that's sticking out would want to go towards the place that's closer to the center.
Okay, so everything being pulled to the center
Yeah.
creates the sphere.
Creates the sphere. Yeah. And that's that's a constant. Once you write down the equation for gravity, that's like just a prediction that when you look out into space, you just see a bunch of round things, right?
If this tabletop here, for scale purposes, was
Yeah.
our universe, so what you're telling me is that our galaxy is here, then the next galaxy is here, but the other galaxy could be up here, one could be down here. It
Could be another direction.
Everything that we see, though, generally, visually, we're shown on, on documentaries and so forth. It all kind of looks like flat to me. You know what I mean? Like, it's being portrayed in a way where there's no depth of the entire space.
Yeah, and
I guess where it's deceiving.
And that is deceiving, because that's definitely, a better depiction would be if they made like an interactive thing that you could fly through, and then you just zoomed around the universe, and you would just, in every direction, you would see things. And actually, like, our galaxy, it does have a sort of plane, but not every galaxy is like that.
Okay.
That has to do with sort of the age and size of our galaxy, that there are galaxies that are more ellipsoidal, that aren't these sort of spirally
Interesting.
armed. There are galaxies that are smaller and more spherical. Yeah.
Is our solar system as a whole, if you look at it from sun all the way out to Pluto, if Pluto's still a planet or not, this week, but
it's not just official. Make sure they're
Pluto's not so Pluto's not a planet anymore.
Pluto's not a planet.
Okay,
Yeah. I could tell you all about that. Too,
we will. I'm old and
okay,
misinformed.
Cool.
So, but as a unit, is our solar system moving through space?
Yes. The sun is making a gigantic orbit around the center of the galaxy, and our solar system is just dragged along with the sun as it goes around the center of the galaxy. And that period is maybe 300 million years, something like that.
And it's going around at the center of the Milky Way, our galaxy. There is a black hole. Is that correct?
Yeah,
so
Sagittarius A is the name of our giant, supermassive black hole.
Okay,
it's like 1 million times the mass of the sun. It's huge.
And the sun is making every 300 million years goes around that black hole.
That's right.
So while we're spinning on our axis and we're also rotating around the sun, collectively our sun is moving us through the galaxy.
Through the galaxy.
Is that right?
The galaxy is careening towards the Andromeda galaxy, and these two galaxies are going to collide
at some
in like
point.
5 billion years. Yeah. And the Andromeda and our galaxy are moving in some local group of galaxies that has some relative motion. So there's relative motions on relative motions. So that's why, like, when we understand space, it makes sense to just be like, motion is a relative thing.
Right.
But that was an insight, again, that took us a really long time to figure out. Like, to Aristotle, who kind of wrote down the first laws of physics that, you know, it's hard to say, but like that survived at least. To him, rest really meant something. Like, not moving was a very special position, and everything in the universe tried to come to rest. And you could do this experimentally. If you push something, it eventually stops. And so to him, this was a privileged state of matter that everything was trying to get to.
Got it.
But Galileo realized, and this was 1400, so this is way later, you know, like 1600 years later, Galileo was like, well, that's just because we're interacting with all sorts of things. That if you weren't interacting with anything, you would just keep going forever. And actually, you would never be able to tell whether you were moving or you were at rest, right? If you were in the description that he uses in his writings is if you're in the hull of a ship, you know, you can't see outside, and the ship is on a perfectly calm sea on a perfectly calm day, drifting parallel to the shore, that you in that hull of the ship, there's nothing you could do to tell whether you were moving with respect to the shore or whether you were completely at rest. He eloquently describes butterflies flying the way that they always would and things like that. Okay, for us now, yeah, when I'm in an airplane, I'm going 500 miles an hour and I'm just like watching Netflix and like eating pretzels. And so I get that. But back then, if you were moving, it was because you were like on a horse or you were like on the ocean and you knew you were moving. And so it took a lot of time before people accepted that there's no such thing as moving or not moving. There's only moving with respect to something else.
Got it.
I feel like I'm at rest. I'm going 30 kilometers per second around the sun right now. That's how fast we're moving. That's 66,000 miles an hour is how fast we're moving with respect to the sun. And I'm just chilling here, drinking water, having a conversation.
Yes.
And that sun is going even faster around the center of the galaxy. So, yeah, motion is a relative thing.
So let's say you had a ballerina that was spinning around on ice, and you remove the ice, you removed everything, you remove everything, the space, and she's spinning, or he's spinning. I saw somewhere in a documentary that if everything was removed, they still would feel being pulled. They still were being pulled. And the question would be, they're being pulled by, in relevance to what exactly?
Yeah.
Does that make any sense?
Yeah. So rotation is a pretty hard one.
Okay.
Like translation, like just moving in one direction, it's clear that if I was the only thing in the universe and I was moving at some velocity, then that would have no meaning.
Okay.
Like moving at a velocity versus being at rest, there's nothing to say with respect to what. Rotation seems kind of weird, right? Because the way that Newton described it was, if I had a bucket of water, I could tell whether that bucket of water was spinning or not, because the wall, like the water on the outside, would start like curving upwards, and it would make sort of this bowl shape. And so even if I was the only thing in the universe, shouldn't that happen? Shouldn't that like, and wouldn't I be able to say I am rotating? Right? And general relativity actually starts to weigh in on this sort of question, to suggest that whether you're rotating or not is sort of fixed by the like stars infinitely far away, that like the universe has some reference frame that's not rotating, and if you're rotating inside of there, then you'll create that. And if literally the only thing in the universe was this bucket that's spinning, that like space-time, all of space-time would be dictated by just this thing, which is the only thing in the universe, which is this rotating bucket, and then presumably maybe it wouldn't actually have like the ballerina wouldn't know that the ballerina was spinning. Do you know what I mean? But I haven't really, you know, seen a really well fleshed out calculation to convince me that that's the case. This guy Mach, M-A-C-H, he was a philosopher / mathematician, actually, and he was one of Einstein's one of the people Einstein was influenced by whenever he was coming up with general relativity. And this Mach guy was one of the people who talked about this sort of like, what does even rotation mean if there's nothing to rotate with respect to? You know, because if you're on a perfectly circular orbit rotating, nothing is changing its relative position with respect to anything else. So there's no positions that are changing, right? It's like what? Yeah.
Let's talk about time.
Okay, cool.
Because I think time is so intimidating that I don't think a lot of people really even think about it because it's so hard to conceptualize. What is the definition of time? We talked about it being another dimension, possibly. Is time another dimension?
Yeah.
And why can't we go back? Why can't we go forward? There's been some experiments, you know, I think they've put devices up on a plane and the plane circled and it's off by like 1/1,000,000th of a second. And
yeah. So definitely, yeah, lots of things to say about time, because time is something that like we still only like kind of understand, and it kind of depends how you're using the word, like in what sense you're using time on what's the best way to talk about it.
Sure.
So in some sense, time is just like an ordering. It's like a sequence of things that, because we have memory, we're able to sort of put them into line, right? And so time is sort of the ordering of like the motion of a hand of a clock, kind of taking back and forth. And that makes it almost like more conceptual than like a dimension, the way that you can go this way or that way or that way. But it's true that our intuition about time, that time is just like something that everything is ticking away in parallel, that's not exactly right. That like there are things that determine the relative rates at which things happen, and that one of those is motion. So this is special relativity, says that if you know you get into a spaceship and you go all the way to Alpha Centauri close to the speed of light and you come back, that you know if you go close to the speed of light, Alpha Centauri is about 4 light years away, so you come back in about 8 years, right? Depending on how fast you went, I could be like 1,000 years old, right? And so this is the twin paradox, and it has to do with how time is affected by relative motion. And then 10 years later, so from 1905 special relativity to 1915 general relativity, Einstein also showed that gravity also affects time, because this curvature is not just a curvature of space, it's a curvature of space-time. And so
space-time is an actual word.
Space-time, no hyphen, no space, just one word, space-time. And that if space-time is curved, then like gravity, or like the presence of matter and energy, should affect the rate at which clocks tick. And GPS would not work if we did not understand the theory of general relativity, that satellites are far enough away from Earth that time legitimately clicks at different rates in space than it does here. That if you live your whole life on the 4th floor and someone else lives their whole life on the 5th floor, that you lived a different amount of like time in some sense, right?
Measurable time, as the way we measure it.
Exactly. So yeah, a really big sort of like not exaggerated, but like the sort of extreme example of this is if you are close to something that's extremely warping of space-time, like a spinning black hole or something like that, then time can really be affected by that. Like, have you seen Interstellar?
I've not. I heard it's very long.
Interstellar's long.
Is it good? You recommend it?
It goes off the rails at the end, but it's still a pretty beautiful and interesting thing. And it was partially written by the guy who like was the lead discovering gravitational waves. Kip Thorne
really
is this legend in physics, and he like kind of came up with the idea for this movie and like worked with other people, and he was one of the executive producers, and he did actual space-time simulations in order to like make the visual effects for it. So scientifically it's actually kind of a cool movie. So one of the things that happens in this movie is there's a planet that's close to a spinning black hole, and they have to go down onto the planet to get something and come back. But they know that it's close enough to the black hole that the guy who stays on the ship is going to experience like 20 years and the time it takes for them to like go down and come back.
Got it.
And so it kind of plays like psychologically with this. Like the character's totally different after they go down and come back, because this is what happens to a person when they're alone on a spaceship for 20 years, right? He's like kind of like this weird monk whenever they come back.
Right.
And also the main character, Matthew McConaughey, you know, he's been getting videos from his daughter on like her life and everything as the movie goes on, but when he goes down close to the black hole and comes back, he has like 20 years of her life that he can like watch the videos of, because and so so time and that special relativity and general relativity imply that time's not exactly what it seems. But then there's also another element of time that's kind of interesting. That's not just sort of like, you know, how do we calculate how long something will take in a given whenever it's close to the Earth or not close to the Earth.
Okay.
There's this sort of fact that if you watched a video of something happening, you would be able to tell me whether that video was in where you're playing it in reverse or you were playing it forward, right? If you were recording this conversation, like you would be able to tell based off of the way that things are moving around. I'd be like spitting water into this thing, you know, like when I do this, I kind of knock this over and it hits the table. But in the reverse video, all of a sudden the table would just bang this thing up and it would just sit like that, right?
Correct.
The laws of physics are completely symmetric. The laws of physics are the same forward in time as they are backwards in time. There's the arrow of time. We keep going forward. There does seem to be a sense in which there is a direction of time that I remember the past, but I don't remember the future. But in principle, there's nothing in the laws of physics that says why that should be the case, right?
Got it.
So this is something that has to do with entropy.
Right.
And
right.
Yeah, and entropy in some sense defines a directionality to time. So there's just like time in terms of intervals of time, but then there's an orientation to time that also is kind of puzzling. So what is entropy?
Right.
A lot of the ways that people describe it is it's like the measure of disorder or something. And yeah, there is like a rigorous mathematical definition to what entropy is. It's basically like how many different microscopic configurations make up a given macroscopic configuration. The easiest example of this is you have a deck of cards, and if you say, you have like a pair or three of a kind, all these poker hands, right? Flush, straight, these things. The things that there are more of, the higher entropy hands, are like one pair. Why is that? Because you could have 2 7s and then all these other cards.
Got it. 2
7s and then different ones. 2 7s and something else. 2 3s and then all these. There's all these different ways to make a pair. But there's only 4 royal flushes. There's a 10 through ace of spades, a 10 through ace of hearts, right? And so the macroscopic configuration is a flush or a straight. The microscopic configuration is how many different straights can I make out of this giant pile of cards, right? So entropy is like what are like the number of microscopic states that have the same macroscopic description.
Got it.
So first of all, you have to have 2 different sort of descriptions in order to even talk about this in the first place, right? So that's kind of interesting. And second, how this is connected to disorder is that there's a lot of ways for things to be disordered, but there's not a lot of ways for things to be ordered, generally. There are exceptions to this, which is why it's not a perfect analogy, this order and chaos thing. But generally, there's like a lot of different ways for there to just be like random mess and disorder. But if you, for example, there's only one configuration where all of the gas particles in this room are just like in 1 little cubic centimeter in the corner of the room. In principle, there's nothing physically stopping that from happening.
Right.
There's no physics that stops all the particles from randomly finding their way into that corner, and then all of us like suffocating. But the reason it doesn't happen is because that's a low entropy state. The high entropy state is for there to roughly be the same amount of gas in any given little patch of the room. Right? And so the arrow of time comes about from the fact that if you just let random things happen, and your system is big enough and complicated enough, everything will tend to increase its entropy, because everything will tend to find itself into the configurations that are more likely, that there are more of, right? That if the most common thing is to have none of these flushes or straights or anything like that, then if you had millions of decks of cards and you just dealt out hands everywhere and you just picked a random hand, the most likely hand you'd get is the one that has no special features.
Got it.
Right?
Got it.
And so that's what entropy is. Entropy is basically how big is this sort of phase space? How big is the space of possibilities that represents this particular situation?
Right.
And entropy always increasing just means that you're always more likely to find yourself into one of these bigger spaces than one of these smaller spaces.
Got it.
And so that defines a sort of directionality to time, because as things evolve forward in time, they increase entropy. As you go back, they decrease entropy. Right.
Do you think the science will ever become available? And I don't know when, but do you think it's possible that we will be able to play with time in a real useful way? Or would it be useful if we had that ability?
Yeah. So definitely, we already play with time with GPS. I mean, like we already are like having to like tweak calculations inside of your phone to figure out where you are because of the fact that time is ticking differently. And one useful thing about this is, so one thing that's sad about the universe is that it's really big and that we don't live very long, right? So if the next galaxy is 1 to 2 million light years away, even going the speed of light, it should take 1 to 2 million years to get there, right? And the answer is no, actually, because if we're going close to the speed of light, time isn't ticking very fast for us. So we can get there in 10 minutes. Right? But what happens is, if we came back and wanted to tell our friends, yo, I just went to the Andromeda Galaxy, it was super cool, we get back and like there would just be a different species of creature living on a different Earth with different like continents. And so there's at least that aspect in which like this kind of ambiguity, kind of changingness of time we could kind of use to our advantage, and that like we can't actually have a sort of Star Trek like thing. It's just that there would be an asynchronousness to it, that like one civilization would go off to a far part of the and it's not like they would like be warping back and like see their friends at home. It's just like they'd be in a completely disconnected part of the universe in that sense.
Yeah, because coming back, they'd be coming back to a completely different planet,
to a distant future. The planet might be absorbed by the sun after it ran out of
hydrogen
gas.
Be a planet.
So now so the next question is like, what about back in time? And so what would it mean to go backwards in time? And for that, I mean, that's almost like, could you build something that just reverses the sort of like directions of everything, so that way you reconstruct past configurations? And the answer is like, well, maybe, but that would like destroy whatever the current configuration is in some sense. So it doesn't, time travel never really made sense to me. It's not like there are parallel lines of past and future that are happening simultaneously that you can kind of hop from one to the other in principle. Now, there's the whole many worlds thing that we could get into.
Yeah, well, I wanted to go there next, actually. And that's where, but there was that theory about you go back and you kill your grandfather, that, you know, and then would you still exist?
To me,
the quandary of that.
I feel like I don't even know enough about what it would mean to go back in time to really feel like I could answer that question. I could imagine there being multiple branches of a wave function, which we'll talk about when we get to the many worlds thing. One in which a system that resembles my grandfather exists, one in which I'm like here sitting in this podcast room, right? And if I found myself on this branch and killed my grandfather, like, no, I wouldn't die, because we're kind of on two separate planes in some sense, right? And so in that sense, I wouldn't even really call that as back in time. I would call that as over to another place that is similar to a memory I have of my place. And so I don't think there'd be a sort of like grandfather paradox in that situation.
Now, you mentioned many worlds. So these examples of people trying to explain the Big Bang Theory, because, you know, when people say, I believe in the many worlds theory, what is that?
So there's two distinct things that often get sort of mixed together.
Okay.
So I can talk about both of them. So one has to do with the Big Bang and string theory and things like that, where you could have many universes, right? You could have a multiverse, if you will, right? And that, like, the bigger 10-dimensional universe, it's big enough to have many of these multiverses. Some might be 4-dimensional, and some might have laws of physics that look very much like our laws. And string theory essentially predicts this, in a sense. That string theory, it's not that it predicts it, it's that you could fit all of these multiverses inside of string theory, and there's no reason why, you know, there wouldn't be some manifestation of all these different solutions of string theory. Right? And so people use this actually to describe certain things. It's called the anthropic principle. And it's this idea that some of the answers to some of the deepest questions we have might not have a solution like, oh, if you do string theory and you do the calculation, you'll get this number. That some of the questions, like why is the mass of the electron what it is, or why is the mass of the Higgs boson what it is, some, you know, people say that, well, the answer to that question might be, that's just because this is the region of the multiverse we live in. And if the mass weren't like that, then chemistry wouldn't exist, and people wouldn't exist, and we wouldn't be here to ask that question. And that's why it's anthropic, because it's like, it's basically our own, the fact that there are living, thinking creatures asking these questions sort of selects which regions of the multiverse are livable.
Got it.
And so things might be the way they are, not because of some deep calculation that you do, but because it's an environmental parameter that allows for people to exist.
Got it.
An analogy would be like, you know, in the 1800s, people tried to calculate why the planets were where they were, why Mars was this far away, Earth was this far away, Venus was this far away. And nowadays, we know that there are trillions and trillions of stars, and each of them probably has about a planet or two, and the planets, it's just a random thing, that it's an environmental parameter. So why is the Earth so close to a star when it could be anywhere? Well, because we couldn't be anywhere. We could only be close to a star because we need that heat to like evolve and live, right?
Because in the Goldilocks thing, right?
Exactly. We're in the Goldilocks.
We're in the perfect location
not
to
too hot,
prohibit us to exist.
not too cold. Yep. So yeah, exactly. So like there are things that we accept already under the anthropic principle.
Got it.
That space is really big. There's not a whole lot of region of space that's close to a star on a small rocky planet, yet here we are. But of course, where else could we be, right? We couldn't be floating in the middle of space. And so some people think some of the fundamental parameters of the laws of physics are like that. That they could be anything because string theory admits a multiverse of different things.
Got it.
And that only certain multiverses would have enough time to evolve structures like galaxies and stars and have the right chemistry to create like carbon chains and complex molecules that could integrate information in a way that led to like conscious thinking creatures. And so those regions of the multiverse must be, you know, where we should find ourselves. And in 1988, 1989, Steven Weinberg actually predicted roughly what the parameter for dark energy should be before anybody thought dark energy was there. Before anybody measured it, he said, well, there's no reason why it shouldn't be there. So maybe why we can't see it is because it has to take a specific value in order for the universe not to just accelerate apart.
To exist
and if you calculate you know, how big should it be so that way galaxies form and people form to ask this question, he ended up getting pretty close to the actual value just from that anthropic kind of argument. So that's one thing. The multiverse has to do with the fact that different regions of the universe could populate different physicses, like you know. But many worlds is an interpretation of quantum mechanics. So many worlds is something that's a little different. You could believe in one and not the other, or vice versa, right? They don't depend on each other. So the thing that describes the universe in quantum mechanics is not like a particle that has a position and a location, but it's this thing called a wave function. And it's a mathematical concept that, you know, would kind of take a bit to get into, but generally it's a tool that we have that allows us to calculate probabilities of the outcome of experiments. So if you give me the wave function, I could say with what probability should you see an electron there, with what probability should you see whatever, a spinning photon over here, whatever, right? And it's very conceptually tricky to think about how we go from a world of wave functions to a world of tables and chairs and things like that. And what Niels Bohr and his crew up in Copenhagen and Denmark did is they had this Copenhagen interpretation, which is, okay, the wave function has all these different possibilities, but when you measure something, you collapse the wave function, and it just, all of that probability compresses into the one reality you see, and then the other parts of the wave function just disappear. They don't exist anymore.
Okay.
Right? And there was really no reason to do that. It just like, it allowed us to just ignore the fact that there's this gulf between our theory and our like experience.
Right.
So it had to add this new piece of collapsing wave functions, and like there's no sort of time dynamics of this collapsing wave function. It's just a kind of made up thing, right? So people weren't really happy with it. And this guy Everett in like the 50s, maybe early 60s, he was like, well, what if we didn't collapse the wave function? What if there was just the wave function doing its thing? What would that world look like if you were a person in that world? And what he kind of came up with was like, well, we are all particles, and particles have like positions and locations as sort of branches of the wave function, and so we are sort of on a brand. If we're made of stuff, which, you know, if you're a materialist, you believe we're made of things, then we must be like, you know, on some branch of this wave function. And the fact that there's probability in quantum mechanics is not because quantum mechanics is like God playing dice, is some like non-deterministic thing. It's because when we do an experiment, we don't know which us we're going to be.
Got it.
Right? It's more the uncertainty of which like Coop I'm going to become when I open this box.
Got it.
Right? That I'm going to sort of like relate to when I open this box that creates this probability. And so Sean Carroll is someone that you know, you mentioned in an earlier discussion. Sean Carroll has been really trying to push that, like, really the many worlds thing, where there are like many versions of you, and that's kind of like the simplest theory of quantum mechanics, because it's the only theory that just takes quantum mechanics for what it is and doesn't add all of this extra superfluous stuff. It's just like, you just have to accept the fact that you are a quantum system. And so if there are sort of, you know, many different ways that you could be, and they're all in some superposition with each other, then there are many different yous in these superpositions. Like, so, you know, you can entangle yourself with a system that is in a quantum superposition. This is Schrodinger's cat. You could take a macroscopic thing like a cat, and whether it's alive or dead, you can entangle with like a radioactive decaying particle that's in some quantum superposition. And so that cat, you have to say, if you believe in quantum mechanics, that that cat is in a superposition, right? And so, yeah, that's kind of where many worlds comes in. It's just that our experience is in some sense one possibility of a much larger thing. And what's kind of interesting is these worlds aren't like totally parallel. Like, it's not like you can't ever interact with another world, because there's quantum interference. That's what this sort of double slit experiment tells us, that that's not just about light. If you shot a proton into a screen with two slits in it, that you'll get a pattern. If you fire a bunch of them, you'll get a pattern that looks like, even if you shot one at a time, that looks like the proton interfered with itself. And what it is there's one world in which it goes like this, one world in which it goes like this, and those two worlds can interfere to create this interference pattern.
Wow.
And so, yeah, it's we're still, I think that like it's coming back around. People are starting to like take it more seriously now.
Okay.
And I think that will be something that will be pretty interesting over the next 20 years, is I think we're going to be slowly digesting quantum mechanics a little more and being like, whoa, actually, we wanted to kind of keep our nice classical picture, but just have the math of quantum mechanics help us make predictions. But we should actually maybe throw away this nice classical picture and think about what it would really mean to exist as a quantum superposition or something like that, right?
So essentially, is the position of many worlds, like if I decide to bang on this table, that sent the direction of this conversation, and from my perspective, this way. Had I went up and slammed that door and came back and sat down, the rest of them would have went in a different direction. Does all of those worlds exist?
Yeah.
Every option we do or take or do not take, the opposite of what we didn't do existed. We did do it. Not just in the plane that we're in. Does that make any sense?
Yes, definitely. Yeah, and in some sense, we have to.
That's mind.
If we want to be, if we want to be careful, we have to unpack exist and like what it means for something to exist versus not exist.
Okay.
Because it's not like you can like go talk to this person that said something else. It's not like you can like.
Well, that's the science fiction. That's Hollywood for
exactly.
Right.
Yeah, and so like in that sense, it doesn't exist in the sense that it has this sort of like causal interaction with you in that sort of way, but two different worlds do interfere in this sort of like quantum interference way. Like I said, the photon going here and the proton going here interferes. And so, yeah, I would say yes, they exist, because to me, it's the wave function that exists. And talking about these conversations and stuff, those are just certain sort of branches of this wave function, which has all of these possibilities as things.
That's deep. So,
yeah. It's kind of
for a layman like myself. That's very deep.
It's deep for everybody. It gets deeper the better you understand it. So it doesn't get any like it doesn't become normal at any point, I guess.
Do we? For, the Big Bang is. We could do a whole show on that itself. The essence of the Big Bang is: are we able to look back in time and do the math, like just all the way back to just a couple seconds after it happened?
Yeah.
But we can't go all the way back.
Yeah.
Is that right?
And that's right. And that's why, like earlier you said, like it kind of things came out of nothing. But we have to be careful because we have to be agnostic about what happens before this moment. Like, but as soon as our, equations and theories break down, then if you're being a good scientist, you have to be like, I have some intuition maybe about what happens, but I can't say with any confidence what happens at that point. So yeah, the Big Bang is just the following. And originally it was a pejorative term. It was to make fun of the idea. Some big bang happened, right? And then it kind of stuck. It was kind of funny. But
there was no bang at all because there was no sound, right? I mean, there is no. If we happen to be in a spaceship there watching it unfold. There was no sound. There was nothing.
Watching the Big Bang unfold is an interesting concept because if you're in a spaceship in the universe, you are experiencing the Big Bang happened everywhere in the universe at the same time and at the same place.
And that's a hard thing to grasp,
So basically, Einstein has this theory about how gravity is affected by matter and energy. So if you tell me how matter and energy is wiggling over here, I'll tell you how gravity is affected by that. That's true of small things. That's true of big things. And you could discuss the whole universe, right, and how the whole universe should evolve if it's full of matter and energy. So with general relativity, we could now have an actual mathematical cosmology. Like cosmology originally was more about like literature and myths and religions and things like that were basically, it had nothing to do with science and math. Like it was about, cosmology was origin stories and things like that. But now we have a mathematical theory that talks about the universe with a capital U, like with everything. So people started to be like, okay, what does this say? We have this theory. What does it say? And what we see is that there's relative motion of all of these galaxies with respect to each other, and things are sort of like drifting further and further apart, and space is sort of expanding, right? We assumed at first that expansion was slowing down, but it turns out that expansion is accelerating.
Who was the scientist looked in the telescope and realized everything was speeding up, was accelerating? In California was his name. Oh my gosh, was it Kepler?
So there's a couple things that this could be. So Hubble was one who saw that, the further away things were, the faster they were going,
traveling,
which says that there's expansion.
Right.
But then it was actually some folks at Berkeley in the 90s that realized that expansion was accelerating. That it's not just expanding, and it's not just like it's kind of like... It's like it's like kind of speeding up.
It's still speeding up.
It's still speeding up, yeah.
So at some point, do we anticipate it's going to slow down? Could it contract back on each other? Back on everything?
Yeah, so that's what we don't know. Because the mechanism by which it's speeding up, our best description of it is called dark energy. And our theory of dark energy is that it's just a overall constant energy density that is uniform, constant, and everywhere in the universe. And if that's true, it'll keep expanding forever.
Wow.
But if it is not constant, if it's changing in time, it's just changing too slowly for us to notice, then things could change. And so we're working on that. That's like dark energy is one of the biggest kind of puzzles. But that's forward. Let's go backwards because we're talking about the Big Bang, right?
Yeah, yeah.
So you could run the numbers and you could say, well, what happens in the other direction? Remember, physics is completely symmetric in time.
I never looked at that
So
way.
like if I could like predict what's going forward, I should be able to run the clock backwards too.
Right.
Time goes in the direction.
Right.
And if you kind of turn it back, you get a contraction. And what you see is that it doesn't just sort of like asymptotically contract forever. There is a finite time in the past that the distance between any two things should go to zero. Everything in the universe, right?
Okay.
There should be a singularity in the sense that everything contracts to a point.
Right.
And this is like in your first year graduate school class on general relativity. I remember the day that I got a homework assignment that was like calculate the age of the universe, which is like a totally crazy thing to get on like your homework.
Sure.
Right. And that's where this like 13.7 whatever billion years number comes from. It kind of changes depending on the value of dark energy, and we're getting better at measuring it. So, but anyways, it's something like 14 billion years, right? You can go backwards in time, and as you go back, things contract, and as they contract, things heat up. Just like how a car, when a piston compresses the air-fuel mixture, it eventually gets hot enough that it combusts and explodes.
Right.
As it explodes, it cools. And so when you, in the other direction, space expanding gets colder, which is why space is so cold. Space is 2.7 degrees above absolute zero.
Got it.
Right, so negative 270 degrees Celsius. Why is this so cold? Because it's been expanding for so long.
Understood.
Right? So if you're contracting for a long time, it heats up and heats up and heats up, and it eventually heats up to a point where atoms can't even form. That it's so hot, the electron has too much energy to just be going around in circles around the proton. It just flies right past it, right?
Got it.
Whenever you don't form atoms and you just have charged particles everywhere, then light can't just propagate in a straight line.
Understood.
Right? It bounces off of all these charged particles.
Right.
So at that point, back whenever it gets so hot that there aren't atoms, we can no longer see anything with telescopes. And this is why gravitational waves are so important, because if we want to see something before that, we need something that can see through this plasma. Right? So this is called the cosmic microwave background, is like seeing the surface in time.
Well, I saw that
all directions.
picture, right?
Yeah,
it's based on the color map, right?
Yeah, so that picture is like a picture in every direction of what it looked like in the universe, only maybe 100,000 years after the Big Bang or something, whenever that was like things cold enough in order to form atoms. But you can go back further, and our theory allows you to do that. Our observation doesn't, but our theory allows you to go back further. So you could keep going
further back?
So you can keep going back, and our theories of particle physics are good enough now that we understand what happens whenever even the protons can't exist because it's so hot. So the quarks that make up the protons are just freely flying around. And you could keep going back until fractions of a second. And so you might, if you believe the standard model is good all the way until gravity comes into play, then you can go back to what's called like a Planck time, which is like 10 to the minus 40 seconds or something like that. It was 43 seconds. So a really long time ago. But I suspect that there is more to physics in between the scale at which the standard model is true and the scale at which gravity becomes important. There's probably, maybe not supersymmetry, maybe supersymmetry. There's probably other particles, though. So we might not know for sure, right? But we could at least go back really far, like to within, 10 to the minus 20 seconds or something like that. Right? But past that, we don't know. Because eventually, as things get compressed so much and are so hot and energetic, that actually the particle's own effect on the space-time, like the energy of that heat itself is interacting with the space-time, and that interaction has to be quantum mechanical in some sense, and we don't have a quantum theory of gravity. And so some people think that there maybe was a sort of like bounce, or like the universe sort of like contracted to some like Planck scale and then like expanded again, and that it just constantly does this like back and forth and has done that forever.
And we're just living in one of
one of these bounces, and there are people who are looking for.
What's that called? What's that theory called? bounce theory.
Yeah, I mean, like the big bounce is how people have talked
really?
about it. Yeah,
I've never heard that one before.
So there's a guy, Roger Penrose, who
heard the name.
Yeah, he was like a contemporary of Stephen Hawking, so he's a pretty old guy from the UK. And Penrose Hawking radiation, like he was part of that all that black hole radiation stuff. He actually has a theory of the sort of pre-Big Bang and post-Big Bang, and he says that the cosmic microwave background should actually reveal some structure that would only be there if there was this sort of like bouncing moment. And he's like looking for that. He has graduate students that are like looking for that structure. So there are like some theories that have some kind of predictions, but we're not really. So
that bounce theory, so I'm just throwing arbitrary numbers. So maybe like every 120 billion years, there's a cycle, right? It's at its lowest, and then it bounces outward for, let's say, 120 billion years, and then it comes. Would it come back faster than it expanded?
If you believe in energy conservation, then probably not. Probably it would be just like a perfect bouncy ball that kind of is dropping, right?
Okay.
But yeah, so if the cosmological constant that is dictating the expansion due to dark energy, if that's not constant and that slows down and then things stop and then gravity kicks in and starts pulling it back together, then yeah, that could be our fate. Another example is we could be living in a false vacuum.
What is that?
What is a false vacuum?
Yeah.
Right. So empty space isn't completely empty.
I was going to ask you that. I forgot.
Yeah. So it's basically empty space is more the lowest energy state of all of the fundamental quantum fields of nature. And so I know it's not empty because no matter where I am in space, if I, just do this hard enough with enough energy, I'll create all sorts of like particles. That actually particles, because of Heisenberg's uncertainty principle, that like energy can be created, but just for a short amount of time before it disappears, because there's an energy time uncertainty principle.
Right.
That particles and antiparticles can kind of pop into existence and then re-collide and then disappear.
Okay.
And you might say, well, can we see them? And the answer is like, well, no, because they disappear before you could see them. And then it's like, well, now this is like angels dancing on the head of a pin. Like, what? How do I know they're there?
Right.
Well, they actually have a measurable effect. Okay.
Okay.
So this is called the Lamb shift, and we calculated it and measured it in the 50s, and this is kind of what kick-started this whole standard model quest, in the sense that this is when people really started taking quantum field theory seriously, and that's what led to all of particle physics. So imagine that the universe was filled with a roiling sea of particles and antiparticles popping in and out of existence. But imagine that they pop in and out of existence in timescales that are like way too short for you to actually like detect one of these particles. What would be the effect of that? Well, an electron and a positron, a particle and an antiparticle, one's negative and one's positive, right? So let's say you have some positively charged particle in space, right? Some proton just sitting here. And imagine all around it, there are electron-positron pairs popping in and out of existence constantly.
Okay.
Well, what happens is the electrons want to be closer to the proton, and the positrons want to be further away from the proton, because likes repel, right? Opposites attract. And so they don't pop in and out of existence evenly. That like they'll pop in and out of existence so that the minuses will want to point towards the proton and the positives will want to point away from it. So what that means is the vacuum behaves like in what electronics we call a dielectric. And a dielectric is something that you like can put in between two plates of a capacitor to increase its capacitance.
Right.
What's a dielectric? It's basically if you put an electric field through a neutral atom, so it's neutral, so it doesn't move, but it still has some positive charge or some negative charge going around it. What happens is the positive charge moves slightly away from plus, and the negative charge moves slightly away from negative. And so you get something that's kind of more plus on one side and more minus on the other.
Got it.
Water is the same way. Water is H2O. The two hydrogens are a little bit more positive, and the oxygen is a little bit more negative, which means water is polar. It has a sort of negative side and a positive side, which makes it stick to itself, which is when you pull your hand out of the water, sticky. So the vacuum must be filled with this polar particle and antiparticle pairs. And what it would do is it would screen the electric field of the proton. because you would be seeing the electric field of the proton, but it would be blocked by these electron-positron pairs that are oriented in the opposite direction to try and screen it, right? And so what that means is as you got closer and closer to a proton, the field should get bigger and bigger because you're going through the sea of electron-positron pairs. And that effect actually changes the location of electron orbits as they go around protons. It's like the hydrogen is a proton with an electron going around it. This slight change in the orbit due to the creation and annihilation of particles and antiparticles is called the Lamb shift. There's some guy named Lamb. And it's a shift in the sense that the orbit is just a little bit closer because it's the force is a little bit stronger than you'd expect. It's weighted. Right? So anyways, these things exist, and the vacuum is made out of these things. And the lowest energy state is what we call the vacuum. So like, you know, a particle is an excited state above the vacuum, which is so emptiness is really just lowest energy. Now, in principle, there could be another energy state that's lower than the vacuum, that has less energy, but there's just no sort of continuous way to get there. So imagine like a hill, and then a valley, and then another hill, and then a deeper valley. If you were in this little hill here, you would say you were in the lowest state. If you go left, you get higher. If you go right, you get higher, right? But imagine there was something, maybe quantum tunneling, that allowed you to tunnel to this lower state. All of a sudden, you would create a lower vacuum. And everything would fall into this lower vacuum. And what that would look like is it would look like empty space, and then a new empty space sort of like expanding inside of it that has different properties and particles, and all of the energy density of this empty space would be converted into particles of the new empty space. And so the Big Bang could in principle be that too. It could have been an event. And what's kind of freaky about it is like quantum tunneling is a random process. That quantum tunneling is a process that if you have a situation where you have two states like that, there's just some probability of this going here, and you can't predict when it's going to happen. It's proportional to the relative difference and how high the hill is in between, but it's just something that I could give you a probability for, but I can't tell you when. So at any moment, there could be a true vacuum, or truer than the false vacuum we live in, that just appears, and it would literally just expand at the speed of light and consume everything in the universe. And so this is
horrifying.
It's horrifying, but here's the plus side of it.
There's a plus side.
I mean, I wouldn't know if they're called the plus side. There's a kind of a silver lining, and that's that it expands. You could actually work out the math of this. This is a calculable theory. It's not just kind of an idea. It expands at the speed of light. And we call the speed of light because light was the first thing that went that fast, but you shouldn't think of the speed of light as having anything to do with light in particular.
Just a measurement.
That the speed of light is like the speed of causation. That
the speed of causation.
Things can influence each other at that speed. And the lighter you are, the closer to that speed you can get. The more energy you have, the closer to that speed you can get. Light happens to be massless, so it's traveling at that speed. Gravitational waves travel at that speed. Electrons are light, so they travel close to that speed, but they still have some mass, and so they need energy to get up there. But the speed of light is really the speed of causation, and there are some things that can travel at the speed of causation. So if this thing is expanding at the speed of causation, expanding at the speed of influence, there's no way that it could happen and that you would ever notice it, right? Because it would be literally instant in any sense of the word instant, because like causally there's no way you could like see it. It would have to send you a signal faster than it's traveling, which it can't, right? And so we would never know. And we
just cease to exist.
Exactly. If we really want to cook our noodle a little bit here. So this is a random quantum process. So there are many branches of the wave function. Some in which this happens, some in which this doesn't. So this could be constantly happening, and we, by the anthropic principle, just happen to find ourselves in the region of the universe where this didn't quite take us out yet. And so this might happen to me in 3 seconds and I'm gone. But there is a branch of me who now has been 3 seconds, who exists, who didn't get absorbed into this false vacuum.
Got it.
So the many worlds sort of allows for a sort of like infinite versions of yourself that are constantly being like consumed by like vacuum fluctuations.
Oh my god,
it's kind of great.
Oh my god.
It kind of reminds me. Have you seen The Prestige? It's this movie.
Oh my gosh, I did. I was like, it's probably 15
It's a long
years
time
old,
ago,
right?
yeah. But yeah,
there was time travel in there or something?
it was some. I think so. It's been a while, but I'm pretty sure it was that Christian Bale was a magician who could clone himself, and the way he did a magic trick was he cloned himself and then killed himself.
Yes.
So that way the clone lived on, and it looked like he teleported, but really he just fell into like a chamber and drowned. And then and so it's kind of like the branches are just like constant versions of yourself. And like versions of yourself could be dropping off left and right, and you wouldn't really know because, of course, the live you is always the one that survives in this branch.
Science is actually is stranger and actually more fascinating than Hollywood can even spin it.
It's hard to even make something as crazy as science.
Now there was another version of causation of the Big Bang was that there was planes. We were like, and they would collide.
Yeah, these D brains that were. Yeah.
Is that still even like a relatively thought as a possibility?
Yeah. So like in string theory, because you have 10 dimensions, you can have all sorts of like lower dimensional objects in them. So you could have like 2 4-dimensional objects that are floating around in this 10-dimensional space, like 2 2-dimensional pieces of paper floating around in a 3-dimensional space.
Okay.
And then the thing that causes like inflation. If you really believe in things being particles and particle physics, then there should be a particle that is like sort of determining how long inflation lasts and how fast it is and everything.
And that was the gentleman from the 70s.
So
who was the inflation?
Alan Guth was one of the big. Yeah,
that's it.
So this particle that just got named the inflaton, and so one of the things that string theory tries to do is describe inflation, describe the inflaton.
Right.
And because that was like the Big Bang, I guess, is kind of when inflation's like slowed down to a point that now particles can start to like be, because the energy from the inflaton can reheat into all of these particles, and that's really what you call the Big Bang. Inflation kind of happened before the Big Bang in some sense. So what you mean by the Big Bang is kind of you have to be very precise. But anyways, so how did the sort of inflation start, which led into like the Big Bang?
Right.
String theory, one of these models of string theory has this idea of these 2 D brains that sort of like collide with each other, and at the point of interaction is where the inflaton like creates this like inflating universe, and the relative like distance of these D brains is related to like, I don't know, like the mass or energy of the inflaton, something like that. I think it's called the Randall-Sundrum model, maybe.
I've heard that.
Lisa Randall is like a famous
Lisa,
string theorist from Harvard. And so I'm pretty sure that was their idea. But yeah, when I was in graduate school, I learned a lot about string theory, but I was never like an active string theory research. I did strings as like quantum mechanical systems, but not so much strings as in their application to like the origins of the universe. That quantum chromodynamics, like there's a reason why we invented string theory to describe quantum chromodynamics. Mesons act like these sort of like strings of electric energy in some ways, and so just describing strings of energy it leads to a lot of really interesting dynamics. And so a lot of my research was about these sort of, not electric, chromoelectric, these like flux tubes of energy between quarks. So string theory has applications that have nothing to do with quantum gravity. It's like a very interesting mathematical model, and people in condensed matter physics, like material science, like they're starting to use results from string theory. There's this thing called the ADS-CFT correspondence.
What's that?
So this is probably one of the most widely cited papers in like the history of physics. Was this paper in the 90s by this guy Juan Maldacena, where playing with string theory, he realized that there was this complete map, this dictionary between a theory of quantum gravity on one end, and then a lower dimensional non-gravitational theory that's called a conformal field theory. So conformal field theory is basically a field theory, which is like what's particle physics is a field theory, but it has a special property called conformal symmetry. And it has to kind of do with like scale symmetry. Like there's a sort of symmetry between things being stretched out and contracted. So ADS stands for anti-de Sitter, and that was the description of this gravity theory. So you could have a dark energy that is positive, which is like the cosmological constant that we have in our universe, or you could have a dark energy that's negative, and that's called anti-de Sitter space. Okay. So the ADS-CFT correspondence is a correspondence between ADS, anti-de Sitter space, and CFT, a conformal field theory. Okay. One is like 4-dimensional, one is 3-dimensional, or 5-dimensional and 4-dimensional. Like one is there, and so this is really interesting for like material science people because they have a lot of these sort of conformal theories. Right. And what that means is that there's a sort of dual theory of gravity that describes the same physics that this theory describes. And so there are people who are like writing papers about black holes and all sorts of like gravity stuff, but when trying to talk about like the surface of a semiconductor or something like that. So it's kind of crazy. So that has nothing. So anyways, string theory basically, it's been very fruitful in the kind of mathematical models that it's sort of given us, and it has given us a good proof of concept that gravity and quantum mechanics can be put together. Whether it's the theory of everything, I think at this point is kind of irrelevant. It's like string theory was a path we had to go through to get to whatever we're going to get to, and whatever we get to, it might be related to string theory, and we might still even call it string theory, because what we call string theory has changed over time.
Absolutely. Too. Oh, absolutely.
So, yeah. So a common question I get, like, is string theory right? And it's like, string theory is almost right by definition, because the thing that we find we might just call it string theory, because it probably will have evolved out of string theory or something like that.
If you, boy, I'll tell you, this was so good. Are we going to be able to keep working on the math to the very point of the singularity? Are we going to get better understanding of what happened? Are we headed in that direction? Or have we hit a roadblock at 5 years ago and we haven't made any progress since?
Yeah. I think that we are making a ton of progress in like every direction right now. Okay. By every direction, I mean like energy scales, like we're learning a lot about high energy, a lot about low energy. Conceptual directions, like we're learning a lot about like biology, and we're learning a lot about like complex systems versus and our technology is just like going out of control right now because of our like ability to create like very detailed structures at the quantum level. So yeah, I mean, everybody probably feels like they live in some sort of like amazing time. You know, people in the 1600s are probably just like, look, like whale wax, it lasts forever. But like, yeah, but yeah, like right now really does seem like we are just like every single day there's like a new thing that's like, what? It's like totally, I mean, like we just took a picture of like, you know, the event horizon of a black hole recently. Like, I know. There's just crazy stuff happening. So I think that, yeah, as long as we don't all kill each other, we're gonna still continue to make a lot of progress. We are limited creatures. Like our biology limits us, our time scales limit us, our resources, our energies. Yeah, these things limit us. We might overcome some of those limits if we kind of replace ourselves with AI or something like that, right? You know, who knows whether we keep our own sort of conscious experience and just alter our bodies, or whether we just create a new thinking thing that just kind of surpasses who really knows. But yeah, I think that there's still a lot of work to be done, and that we're in really interesting times, and that if you really care about this stuff, I think something that's like really important is that we now have the ability that we could all kill ourselves.
Yeah,
we now have the ability,
no question,
with atomic weapons, things like that. Like we just have to make sure that we're still sort of like politically collaborative enough that we can kind of keep this project going, that we find solutions to problems that don't require force, because as we get our better understanding of the universe, we get better and better of understanding of force, of like weapons and things like that. And so this is one thing that's scary about not seeing aliens. Like we look out into the universe and we don't see anything that even resembles life, and life might be really uncommon, and that might just be like, well, it's only been around for 15 billion years, maybe it's just not very common. But the other alternative is maybe it's common, and maybe as you understand the universe more and more, you also understand how to destroy each other more and more.
Yeah.
And that it's inevitable that like something will happen. Because we came pretty close a couple of times in the last century. And yeah, so
humans.
Yeah, humans. Yeah. We're a tough nut to
let me before you wrap up here, let me ask you just because of course, how could I not ask you this question? Do you believe that there is, as life as we know it, whatever we define biology to be, do you believe that there's other kinds of life out there? Does the math point that it's an absolute truth? There's too much out there for it not to be true?
Yeah, that's the way that I lean, for sure. That like I don't like first of all, we do not have the understanding of life to be able to make a real probabilistic model to say whether or not it's likely or not. We're just not quite there yet. Like, it's way too complicated. You know, it's unlikely that there's life anywhere in the universe if you just wait for things to randomly arrange themselves into self-replicating objects. But that's not, I think, how it works. I think that there's more to the origins of life than just, well, the first building blocks randomly assembled. Like, I think there's something about the way systems process information that we don't quite have yet.
Okay.
And we're working on it. But I think what the results of that research will be is that life isn't some crazy total miracle. There is something about the laws of physics that make life sort of happen in some significantly complicated system with the source of energy and low entropy and things like that. And so if that's the case, then if there's a lot of places where life could be, then there should be a lot of life. And there are a lot of places where life can be. I mean, that's one of the great things about growing up the time that we have. For thousands of years, we didn't know about more than a couple planets, and now we know that there's about 10 to the 24 stars in the universe, and each one probably has a planet or two around it, right? So there's planets everywhere.
We're starting to understand the scope and size of our universe, and I think that's where I would think the probability of it being something out there is probably it's there.
Yeah,
what it looks like and the scale of it, and that's the thing that it's funny to me when Hollywood would make your alien movies. Of course, the aliens had to be roughly our size and look somewhat like us,
got some eyes,
meaning that, you know, because the scale of some of the things in the universe some of them are a million times bigger than the Earth, right? I mean, there's some rocks out there that are.
Yeah.
So if there is life, that life could be as big as North America.
Yeah.
I mean, one entity could be as big as North America. Could be a breathing, living creature.
Right.
We don't have a scale.
Yeah.
We can't predict.
There are. So we aren't totally in the dark about that sort of thing.
Okay.
Because there are a few things about just how chemistry works.
Okay.
That sort of makes there be a pretty good reason why life is the way it is. And there's actually even simpler things than that. Like, for example, metabolism increases entropy because metabolism participates in the arrow of time, and so entropy is increasing, right? And this increase of entropy at a thermodynamic level means that it creates heat. And so whenever, for a living thing to exist, it has to create heat. That heat changes the local environment in which these chemical reactions are happening. So in order to sort of sustain these chemical reactions, it needs to dissipate that heat.
Correct.
So how does it dissipate heat? Well, heat is created in the volume of the creature, but it's dissipated on the boundary of the creature.
Got it.
So the bigger you grow, your volume grows like the cube of your size, like r 4/3 pi r cubed, the volume of a sphere, but your surface area grows like the square of your size.
Ah, okay.
Right?
Interesting.
And so there's actually kind of a limit. Like, you couldn't have something that was like 20 times the size of like an elephant, because it would just be, the inside of it would actually cook itself. Like, it wouldn't be able to radiate heat.
Okay.
And so, I mean, that's not to say that there aren't mechanisms by which you could have heat exchangers somehow, because we make machines that do it. So but like, there are like certain things that
from the biological
things, thermodynamic things that do suggest that we are in this sort of sweet spot where there's just as many orders of magnitude below us to get down to the atom as there are above us to get out to the size of the universe. And we're kind of in this thing in the middle where like we could have maximum complexity without the sort of like fundamental laws like breaking us down in some sense.
Wow.
So now one thing that I think is definitely true is we are kind of assuming life is this sort of water-based, you know, carbon-based thing. But
that's because we know it.
That's because that's all the life we know is like that. An interesting question is, could there be something that behaves like life that is based off of some completely different chemical that lives in a completely different environment? And so that's why we're really excited to go to Titan, which is the biggest moon of Saturn, and it's a huge moon. It's bigger than Mercury, and it has its own atmosphere and everything. Its atmosphere is denser than Earth's atmosphere. And Titan has weather. It has like clouds and rain and stuff like that, but it's like over 100 degrees below zero. So that rain is not water, it's methane. So they have methane lakes, they have methane rain and stuff, so precipitation. And so then the question there is like, could there be another copy of like life that is kind of methane based instead of carbon based, or it uses like liquid methane as the solvent in which the chemical reactions are happening instead of water? There are reasons why some people have good reasons for saying no. Like water does some pretty amazing stuff that has some properties that are not replicated elsewhere in the periodic table. But there are some people who say that, well, we can maybe get around that, blah blah blah. Yeah, but like one important thing is like it's not like there's new elements out there or something. Like if we look billions of light years away at stars, we see the same colors that come from all the stuff here on Earth. So like it's not like there are some new molecules. Like we can literally sit down and make all of the kind of different molecules and things.
I get it. So you don't think that we're going to find any new elements out there that we are not already aware of? That's right. No.
That all of the stable elements, all of the elements that don't decay on very fast timescales, we've found them all.
Are we just lucky? And the reason I say that is not that we exist, but you see things in space that are just horrifyingly big, like stars exploding, supernovas. And we hear and we learn about these things, but here we are on Earth in this little solar system, far away from these theoretical explosions of mass sizes. We don't have that happening around us. It just wipes out our solar system. Now, a supernova close enough could wipe out our solar system, right?
Easily.
Are we just lucky, or are we looking also as a component of maybe 100 years, if we're lucky, in our lifetime, 80, 100 years, in a scale of 13.7 billion years?
That I think is probably more what it is. That first of all, like yes, like we have a very nice stable, like not only is our star the right temperature, but it's not fluctuating wildly in temperature, and it's a star that'll have a 10 billion year lifespan. Like these are all very important. By the anthropic principle, of course, we should have expected to find ourselves around a star like that. Of course, because where else could we be?
Absolutely,
right? But yeah, I mean, like every 60 million years or so, the Earth gets smashed into by a Mount Everest-sized asteroid, right? And so we're lucky that hasn't happened in the last 20 years, but at the same time, 20 years is nothing compared to 60 million years.
Yeah, so, I think that's,
so I think that like the thing we have to worry about more than false vacuum decay, supernova, and stuff like that, again, is us. Like we have the power to make our planet uninhabitable.
Absolutely.
We have the power to literally kill each other with violence, and like these are things that like if you appreciate the fact that we haven't seen any life anywhere else in the universe yet should really incentivize us. If it is really rare, what if we are the only intelligent things in some 14.6 billion light year radius sphere? Like that would be a real shame to like have some kind of geopolitical power play and like kill ourselves.
Right. Wow.
So, yeah.
Dr. Coop, this was amazing.
I had a blast.
I would love to have you back again.
Anytime. Yep. Have me back.
For sure.
For sure. Yeah.
This
was
my
number. Hit me up.
Absolutely. This is good stuff. Thank you so much. I appreciate it.
Anytime.
All right, friends. We are out.
Bye-bye.
Fingertips above the water, you watch me drown. You could have saved me, but you let me down.